In this lesson, we're going to be looking at the end behavior of a function. And so we start off with the definition. All right, the end behavior of a function describes what the y values of the function are approaching on the positive and negative ends of the function. It's important to understand the notation of this. So it's going to be written in this format, but it will be read as x approaches infinity, y approaches some value. And so that value could be a number or it could be an infinity symbol, but either way, it's approaching from x goes to infinity or x goes to negative infinity. So what it's looking at is, as you read on the right side of the graph, what's y doing? And as you read on the left side of the graph, what is y doing? Graphically, when we look at this first example, we're going to look as x goes to infinity. So on the right side, as these x's keep going up, what are the y values doing? So these y values are going down. So we just write that as x arrow infinity. As x approaches infinity, y is approaching negative infinity because it's going down. So then on the left side, as x goes to negative infinity, y on the left, y is going down as well. So y goes to negative infinity. For the second one here, as x goes to infinity, we are looking on the right side. So as x gets bigger, y is going down, so it's getting smaller, or it's getting more negative there. So y is going to negative infinity. As x goes to negative infinity, y is getting bigger, it's going to positive infinity. And then 3 and 4 here, same situation. As x goes to infinity, so look on the right side of the graph, as x goes to infinity, the y values are going up to positive infinity, so y goes to infinity. And then on the left side, as x goes to negative infinity, y approaches, and this is a little bit different because it's going this way and the y value is staying constant at 4. So in that case, y is approaching 4 because it's staying 4 the whole time. So it doesn't have to always approach an infinity, it can approach a value. All right, as x approaches infinity, y approaches, let's look at number 4. So x goes to infinity, y is also going up, so y goes to infinity. And then as x goes to negative infinity, y is going towards 0. So what's happening here is it's hitting that asymptote, so y is approaching 0. We've talked about exponential functions, and so in an exponential function, that parent function has that horizontal asymptote at y equals 0. So you can write that in there. There's a horizontal asymptote at y equals 0. We're going to talk about asymptotes here in just a second again. But it's approaching 0. It's not actually going to reach 0. It just tells that it's getting closer and closer and closer to that 0 value. So when we're looking at end behavior, we're not worried about what happens in the middle of the function, but rather what's only happening towards the ends of the function. All right, we don't care what's going on here. If it's a polynomial, it may do some dips and turns, but we're not worried about that. We're only worried about the ends of the function. Now, if we look at what asymptotes are, we have horizontal and vertical asymptotes right now. Asymptotes are known as the limiting behavior of a function because they will limit what values are in the domain or in the range. So a horizontal asymptote is that imaginary horizontal line, and it's always in the form of y equals some number. You want to write the equation because it is a horizontal line, so that it's y equals. And it's associated with the function that indicates that a curve is getting toward or heading towards the y value represented by that asymptote as x gets large in a positive or a negative direction. So what that's just saying is If we look at this exponential function, the y values are getting smaller, they're decreasing, and they're getting smaller, but when we look as x gets very big, these values are just kind of flattening out. And that flattening out is where that asymptote is. So it's not always drawn on our graph. You may have to look at what's implied there, but there is a horizontal line at -4. So that horizontal asymptote would be labeled as y equals -4. And we could talk about the end behavior again, just as a review. So as x approaches infinity, in this case, y is approaching -4, because as we get bigger on the x values to the right, the y values are staying closer and closer to -4. As x approaches negative infinity, so we go to the left side, those y values are going up, up, up. So they're going to infinity. All right, we want to find the horizontal asymptote here, and it's already drawn for us. So sometimes you will have the dotted lines already pictured on the graph. But if we look at that asymptote, that horizontal asymptote is at y equals 2. And then we can describe our end behavior as x goes to infinity. As x gets bigger, the y values are approaching 2 on the left or on the right side. So y goes to 2. And as x gets to negative infinity, so on the left, x is going to negative infinity, y is approaching 2 again. So y still is approaching 2. The last one here, it's not drawn. There's no horizontal asymptote that's drawn for us. But there is one if we look at what the y values are doing. So these y values are decreasing, 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 and we can start to see them level out. And so they are approaching 0. And it's happening on the left side as well. So we have a horizontal asymptote, and it's at y equals 0. Again, we could describe our end behavior. So as x goes to infinity, as x goes to the right, y values are approaching 0. And as x goes to the left, our y values are still approaching 0. Now, not every function is going to have a horizontal asymptote. We don't always have asymptotes. If we looked at those polynomial functions, those did not have asymptotes. All right, but exponential is one example that will have a horizontal asymptote. And these rational functions might have a horizontal asymptote. As far as a vertical asymptote goes, it's still an imaginary vertical line, but it's in the form of x equals. So it's x equals some number because it's vertical. It's associated with the function that indicates what x values are not included in the domain, because that's where a function is undefined. All right, so a logarithmic function, we talked about that parent function. Here's a logarithmic example. This logarithmic function will always have a vertical asymptote. And so in this picture, we see a vertical asymptote at -5 on our x-axis. We would write that vertical asymptote as x equals -5. And it's just saying that there's an undefined value there at -5. So -5 is not in the domain of this function. If we looked at this rational function, it has 2 vertical asymptotes, so it might have more than one, but we see one here and here. So we just list out those vertical asymptotes. This one's at -10, so x equals -10, and then we have another one at x equals +10. There is a horizontal asymptote, but we're only listing our vertical ones right now. So as you look at graphs, some of the key features that you want to describe are those asymptotes if there happen to be any.